Hello and welcome to this July 9th edition of the SkyTour LiveStream, coming to you, as always, from the John Zach Memorial Observatory in northwestern Connecticut. Tonight, we're going to explore the beauty and mysteries of the universe, from beautiful double stars orbiting in perpetual cosmic dance to planets that are around other stars. We are going to look for the stars that are hosting these planets, and we'll see it all. As usual, if you have anything you'd like to see or if you want to participate, join the chat room and ask away. Our moderators will be there, ready to listen and eager to help you. So I look forward to it, and the telescope will be up in just a couple seconds. Well, as you heard in the intro, we're going to be looking at some double stars tonight. Right now I have it on our moon, only because it was beautiful coming up above the horizon, and it's just it's about 10 degrees above the horizon now, so we lost all the shimmer pretty much. But while it was shimmering, it was really quite lovely. So, we'll be starting to move around in just a few seconds. I'll wait for some more people to come in. Bill New York Skywatch is also streaming tonight, so he may have some of the people, and you may want to bop back and forth between the two streams. Now, P&K Skywatch, Paul and Keith are actually going to be working with me and Bill, and the three of us are actually going to have a single site that you can go to, where you can click on any one of our streams and check it out for the moment. Stick around in one, or go back and forth between several all night long. Your call. And that's working out. That's almost ready. So we'll have more news about that in coming weeks, probably days more than weeks, but it should be rather interesting. So how are you all doing tonight? I see there's a few of you in the chat room now, and we have Amanda moderating for us tonight. I don't know if she's there. Are you there, Amanda?
I am here.
And she's there. That's great.
Plugging away.
Thank you for being there for me. That's really kind of you to take time out of your evening to watch a telescope looking at the moon.
For the amount that you give to us, not only is it a pleasure to be able to help in any little way, but it's such an honor that you're letting me hang out and learn all these fascinating things, so thank you.
Well, somebody has to take over when I don't want to do it anymore. just
oh my gosh.
Just kidding. Hey, Amanda, that's a question I have for you. Am I right in thinking that each night in the SkyTour LiveStream, there's going to be a certain point where I turn it over to you and you're going to take over and give us the NASA news of the day?
Well, something like that. We were playing with the idea. I just thought it would be a nice backup if you ever had to leave the dome for any moment, if you wanted to take a break on your voice, because with the questions we have, you do a lot of talking to explain it and make sure everyone gets it. Well, make sure I get it, so I appreciate it. So just a backup if you ever needed to take a break or something. Yeah, I could give you some space today in space history.
Well, that's a cool thing. I think I'd like to do that as a feature every time. That was a great idea you had. So we'll do that. And I may not even need a break. And that's not why we're doing it, folks. It's actually just because I thought, and Amanda thought, it'd be a nice little thing to put in the middle of the SkyTour LiveStream, and I think that's kind of cool. There might be other such breaks in the SkyTour as we move along. Like if I need to recalibrate the scope in an emergency, say I bump it and knock it out of alignment, well then I might have to do that.
Exactly, yeah.
Yeah, but I would make sure you understood that that's what I did. I don't try to hide the mistakes. If I make one, I'll just say, I just blew it. Not a problem.
Yeah, so I mean, well, yeah, the today in space history, I just thought it would be interesting because like some of them might be like, this is the first, like today was the day such and such was discovered, and maybe we could even look at it, right? So
Sure, that's a great idea.
depends.
Yeah.
And yeah, and of course for anyone in chat, if I have enough warning before these go live, I could check out like NASA.org, and I like Space Alert and Science Alert and sites like that and stuff, different things. And ooh, what's that across the screen?
Did you see
What
something?
what went across the moon about 30 seconds ago? I just saw something go from
Nice.
the right to the left diagonal.
Okay, that's cool. I missed it. I was in the middle of trying to
Okay. Oh,
bring the chat up.
21:38 is the time.
I'm sure some folks will see it.
21:38. Okay, I'll just put that in.
Okay.
Okay, but no, and again, if people like, if you guys have any ideas of what you'd like to see or hear, let us know.
Absolutely, because I'm all for it, and if I can take a look at it, if I can see it, I will bring it up for you.
Yeah. And I really liked the last week, although we had a few technical issues. I think that was one of the most beneficial streams for me personally, because we had the mnemonic of "Oh, be a fine guy, kiss me," which is great to remember, but to actually go through in order, this is an O star, this is what it's about, this is an A star, and examples, I found that really, really beneficial. So I'm really looking forward to tonight.
Awesome.
I'm getting it. I am getting it, guys. Not slowly, very slowly, but I am getting it.
Yeah, but
thanks to Mark.
One thing you notice though is your echo is missing, isn't it?
Yeah. No delay, which I knew that was the stream issue, but
right. But the echo is gone too, and that is because I worked with Bill New York Skywatcher, and Bill helped me figure out what was wrong with my setup to cause the echo, and I don't think we're going to have that problem anymore. And the other thing is, I actually bought a Wi-Fi microphone, so I will be able to have a mic right on me the whole time. Because right now, the mic you're hearing is on the center of the 150-pound pier in the middle under the telescope. So wherever I am, the sound gets reverberated back, and it sounds like I'm in a little, it sounds like I'm in a bathroom, for crying out loud, or a porta potty.
Or a dome?
Or a dome, yeah. Essentially what it is, and so that in mind, as we move forward, I'll have a wireless mic on me at all times, so you'll be able to hear without any delay. You'll hear my voice, or any echo. You'll hear my voice, the same loudness all the time. So if I'm lucky, it's going to sound like this the whole time, which I think is much better than the other.
It is
much better than hearing this out here, but. It's on its way. It'll be here in a couple days, and I'll implement it immediately.
See, we're getting there.
Yeah.
Once the iron the king said is going to be, I mean, you just wait. I can't wait.
Well, I can't wait because I'm doing it. But I gotta keep on keeping on, and see what happens, and hopefully it'll be all right. I think it's working out okay.
I think it's working out brilliantly, and it's just gonna get so much better and bigger, and I don't know. I really hope it, inspires young people kind of thinking what to do, or gives people something to think about regardless what the career is. Like, there's just so much to keep an open mind and, let the possibilities. I don't know.
Yeah.
I don't know.
And Gary asked in chat, where's the stream from? Gary, it's from the John Zach Memorial Observatory, which is in northwestern Connecticut. It's an 8-foot dome with a 10-inch instrument and a special low-light camera that has a tremendous breadth of capabilities so that we can see the faintest objects or bright objects like the moon without any problem. So I just thought I'd let you know because you had asked, and I have a little chat up. So you can see I can actually darken the moon, and I can then take a photo of the moon, which I'm doing right now, and then I can actually bring up that photo, zoom into it, and look around on the surface and various items, various craters and so forth. Now you have to understand the full moon is really, to me, tremendously unexciting because there's no shadows except, as you can see in the very, very end here, you can see shadows. The very edge, we call it the limb, L-A-M-B, the limb of the moon. There's very few shadows on the general full moon because all the light's coming right back at you. But at the limb, we still can see the craters and you can still see some of the shadows, which is kind of cool. And the motion of the moon in the sky, the way it rises and sets, and the way the light is on it throughout the month, the 28-day cycle of the moon, it completely and utterly refutes and negates the flat Earth theory, which I find ridiculous, and that people have...
What were you looking at on Facebook earlier that got you talking about that already?
Some flat Earth fool. But the thing is, when I watch and I listen to some of these flat Earth theories, okay, as they say, you look at the moon here, right? And they say, well, the moon is just a few thousand miles away, the sun is a few thousand miles away. And not even understanding any kind of physics to indicate that the sun has to be a certain size and mass in order to support fusion, which is what it's doing. And I don't think they refute that. They think fusion is occurring. But they don't understand the physics. That means you have to have a certain mass, and that means a certain size of the lightest gas, hydrogen, in the universe. To be able to have fusion occur at the core, you need to have a mass of overlying atoms of hydrogen that are pressing down and causing enough pressure for fusion to begin at the temperatures that are required of fusion. And I mean, you just want to go from a scientific point of view. That's it. Go from a scientific point of view. And to me, it's like, if you just take it from science, then the flat Earth is impossible because the sun could not possibly be only a few thousand miles away and as small as they say it has to be. There's no star that could be that size. Jupiter has to be 80 times its mass to even be the smallest of stars. So Jupiter is only an 80th of the mass required to be even a small star. So you see, I don't. It's almost ludicrous to even have to debate people like that. I was debating a guy today because he was arguing with me that the pink little lens flares that you see in some of the Google Earth photos are actually craft, and he's identified beings in these craft you see. Well, the problem is they occur on the ground too. I sent him a bunch of them. They show the craft on the ground or superimposed on people because the car was passing by a group of people walking on the side of the road, or in front of a car, and it's like he ignores those selectively, but still says that, well, those are fake. Oh, okay, those are fake lens flares that exactly simulate his real objects that he thinks we're hiding, and now I'm part of the problem, you see. This is what I have to deal with. And it's the same mentality for the flat Earth fools. They do the same thing. When you're science-free, okay, as they are, you can create the rules of the universe any way you like. You can have a star doing nuclear fusion, and it's only a couple thousand feet across, or several thousand feet across. They don't even, they're not encumbered by science, and so anything is possible to them. Well, sadly, the universe doesn't work that way, does it? Doesn't work that way. But hey, what do I know? I'm just an astronomer. I don't have a whole lot of clout when it comes to this. I mean, no one has to believe anything I say. But you're free to look up anything I say. Okay? And I guarantee you that 9.9 times out of 10 you're going to find data that supports what I say and not refutes what I say. But that's just it. Anyway, that's my monologue for tonight.
Well, before we leave the moon,
yeah.
Daryl thinks that I should ask you about cross-quarter moons.
Cross-quarter?
Cross-quarter moons.
I don't know what cross-quarter moons are, Daryl.
Ooh. Okay.
No,
Please
that,
be more specific, Daryl. I'll get back to that. I also wanted to let you know. Oh, I hope I don't mess up the last name. Jude Talaba.
oh, Talaba, yeah. Is she watching?
Talaba. Yeah, is here. So
Awesome.
I wanted to say hello to
That's
her.
great. Jude is
And
Jude is the head of the planetary replica division of FX Models, my company out in Arvada, Colorado, and she's creating, with her talented staff of artists, she's creating all of the large planets that we send out to all these new buildings all across the country. And when I decided to put them basically into business with me, I was never disappointed because Jude used to run a business before, and she just sidled right up to this as if it was second nature, and took a lot of the worry out of my hands. And then when I had a health issue, obviously when I had to go in for surgery a couple of years ago, and then that surgery, went awry, and I had to learn how to talk, walk, and do all these things again, like I'm doing now. Well, when that happened, she and her team took over and made it all work like it, and it never skipped a beat. Our clients never missed a delivery, and everybody was happy. So either that means that I'm useless, or it means that she did a phenomenal job, and I tend to think of the latter.
I would agree. I knew bits and pieces, but I didn't realize she was taking over for you while you were recovering. That's okay. Well, I mean, the link for FX Models Planetary Replica Division on Facebook. Please like and follow. It's already in chat. I'll put it in again later.
Thank you.
They are a proud sponsor of SkyTour LiveStream with Mark D'Antonio. But yes, oh my God, Jude, please, if there's ever anything I can do to help you, please let me know.
There you go. See, and you know what? That's actually the kind of reaction that she instills in people. She's so easy to get along with, and she's so perfect at what she does that there's never a doubt. I've never been more comfortable. I've had people work for me before. Okay, I've had to fire people. I've had to let people go, and it's always been a sad moment. But I had people working for me that became prima donnas, and that was that. I had people working for me that were great, but then suddenly their work ethic just seemed to go away, and I couldn't get anything needed from this particular guy. It's like, wow, what happened there? Then I had people join me that were fantastic model makers, but they were so burdensome with all the personal invasions of privacy that I just couldn't deal with it. It's like, okay, I'm sorry, you gotta go. It's like, I wasn't proud to ever, I didn't want to let anybody go. I didn't want to do any of that, but I had no choice. So Jude comes along, and you know what? I've never had to correct her once. And I look back and say, is that true? And it's true. I mean, look, she's a Cherokee Indian. Okay, she knows her shit, so to speak. Sorry about that.
Don't make me ban you.
Beep. I'm banned from the SkyTour LiveStream forever.
Next investment and a 7-second delay.
Yeah, I think we're gonna have to do that. I apologize for that, folks. I meant to say she knows her stuff, but the wrong word came out. But anyway, so I'm just letting the believe it or not, while this has all been going on, I've been actually doing diagnostic stuff with the system to make sure that we're ready to go on our little tour when I want to go. And I think we will be ready to go here. Is there any other question before we leave the moon? Did anybody else see that object that you said that you saw?
I think someone said they thought maybe it was a fly walking across the screen. I don't know, because it almost looked like maybe a trail of a satellite. Like when you took the picture and we saw that faint like pencil mark.
Yeah.
It was really, really thin like that, but it was bright and it was going right to left diagonally. Almost, I want to say almost right in the middle. Maybe a little more to the left top corner of the moon.
Did it cross the entire moon, or was it?
Yes.
Really?
Yeah, and I don't know, it was going pretty fast for something to be on the screen. Like, that would be really big, like taking up the whole moon, wouldn't it? If it was a fly on the screen?
Oh wait, well, there couldn't be a fly on the screen, even if a fly was on the end of the telescope. It couldn't do that, and we're not looking at. You're not seeing an image of a screen where you could then see something walking or my hand on the screen. This is a full electronic digital image coming straight from, 250 pounds of equipment that are sitting up on this big steel pier. So there's no focal length and no focus point where anything could be seen in the equipment or on the equipment that would show up as an object that you can actually see. And for proof of that, I'll put my hand in front of the telescope here so you can see how the image will look. Okay? I'm putting my hand all the way across the image, okay, and then I'm blocking the image as best I can with my hand, moving it around. Okay? Now I'm done. And you'll see that the image only kind of barely dimmed a little bit. And that's what my full-size hand and my full palm was doing. So it wasn't doing much. So, anything that could be small enough to be seen has to be in the sky and, between me and the moon and passing in front of the moon. Could it have been a bird flying in front of the moon? Like maybe, I don't know. I didn't see it. I didn't see it. But hey, I'm an image analyst guy, so I should be able to figure it out, right? Maybe. And you sent me the time code for where it was, so we can go back and look.
Yeah, it's in the side chat on Skype.
All right.
Oh, and it was Ian, and he said he never said it was a fly. He said it looked like one. He said it was black. I thought it was white. I don't know. It just caught the corner of my eye, and as I was about to say something, it was gone, right? So, but yeah, no, we have the time. We'll look back. It was probably nothing. It was just really fast and really noticeable. Like I said, it was almost like right diagonal through the moon. So, yeah, SB says probably an airplane. It could have been.
Okay.
It seemed. I don't know. We'll see.
Now we'll go back and look. We will. And again, I apologize for the construction traffic that's being waylaid through my area here. I'm shutting off the camera for 1 second. I got to change the battery. So,
Okay.
you could see the battery indicator on the screen there. And that was just, I put that up for you so you could see that I had to change batteries. So you wouldn't think it went away. Okay, now the camera's coming back up. And we should be, and we are. We're back.
Oh, Daryl said I'm much louder than you, which I'm not surprised. Is there any way you could turn my volume down a little bit? Or a lot of it?
Actually, it's your microphone volume you gotta turn down at your end.
Oh.
Which is fine. And I know I'm louder, and it'll be more equal when I get that wireless in here in a couple of days. I'm just constantly adding to upgrade and get these things settled, and the next thing is going to be a wireless headphone, so that I'll be able to hear without having a headphone cable trailing around me every time.
Yeah, here, I'm gonna move my mic away from my voice, from my mouth a little bit, because if I turn my speaker down, then I can't really hear you.
Well, not your speaker, you turn your mic down.
Well, that's what I mean.
Within Skype, you turn your mic down, and that doesn't affect being able to hear me. That's just me. That just takes your source voice and drops the level somewhat. So that's not a big deal. All right. It's pretty. By the way, I got there's a little calculation that I'm going to teach you tonight. If we know the separation of a double star in what we call arc seconds, that's something we talked about a number of times so far, and I'll review. An arc second is, if you take a degree and divide it into arc minutes, there's 60 arc minutes in a degree. And within each minute of arc, there are 60 seconds. So there's 3,600 seconds, okay, in a degree, 60 minutes in a degree. So double stars are usually given a separation in arc seconds. And the first one for tonight is going to be separated by, what do we got here? Separation of 145.2 arc seconds. Okay? And double stars also have another thing, and that's the angle that they appear to each other. That's called a position angle. But we're not going to worry about that. I just want to talk about the separation degrees, the separation in arc. Because there's an old astronomical calculation that you can do that will give you the separation, knowing the distance to the double star. You can actually get the separation in space that the stars are from each other, which is really cool. So there's a calculation we can do to do that now. The calculation is actually very straightforward, and it's something that you learn in astronomy. Well, a variety of ways. You can actually learn it from actual astronomy courses, but you can also learn it later on if you're doing something, all right, with stars. Give you an example. Here it is. The angular separation in arc seconds times the distance to the star divided by a number that seems like magic. It's a number that's 206,265. It's 206,265. That division gives you the physical separation in light years, if the distance is in light years, of the two stars in space. And then you convert those light years to AUs, that is astronomical units, the distance of the Earth to the Sun, in terms of those. And there are 63,241 AU in a light year. So we will be doing a couple of those calculations tonight just to sort of start getting our feet wet with that whole approach. Alright? So.
That was a lot of numbers.
It's a lot of numbers, but don't worry about it because we're going to do it enough so you'll figure it out. And if you don't figure it out, you don't have to know it. It's just something that's for fun. It's not like it's going to be on a test. Alright? So let's go to our first.
Hold on a second.
Yeah.
Hold on a second. Did you say something was the distance between the first thing we're going to look at is 145 arc seconds?
That is correct.
Why wouldn't that be like an arc minute and so many seconds?
Just because of standard, okay?
That's how it's always said, always in seconds?
Yes.
When are minutes ever used?
No, minutes are used, okay? You can put that in terms of arc minutes, but then you gotta put it in terms of minutes and seconds. So rather than put it in 2 units, these are the number of minutes and seconds that these are apart. You put it all in seconds, or you put it all in minutes. You can put it into minutes. Divide 145 by 60. What do you get? Okay, you're gonna get 2 point what?
15.
Are you doing it? Did you do it?
25? No.
Oh, okay.
I'm guessing.
Oh, okay.
I'm rounding up. 120.
145.
25.
145
225.
Divided by 60. Okay. So if you do that number, and I'm sure people in chat are already doing it, then all you do is, that gives you a number of minutes, but it's not even. It's not going to give you an even value. So you put it all in seconds, and that keeps it even. And that's it. That's the reason we do it. It's just to keep it, one simple unit, and it's something that you can then measure. It's not a big deal.
So like how they time like movies by minutes, not like 2 hours and 20 minutes. It's like
there you go, right? Like 137 minutes. Okay.
No, I'm just wondering, the distance between double stars, is that always measured in arc seconds, or is there a big enough gap for it to be measured in arc minutes, or would it be then something else, not a double star?
It's a personal preference sometimes, but mostly it's a standard that people will measure the distance between double stars in arc seconds. Why? Because most of them are only separated by a few arc seconds.
Yeah, okay, that's what I was wondering.
Yeah.
Okay.
The arc second is the most convenient unit. So.
Okay. So this 206,256?
206,265.
265. Okay, what is that?
Well, that number is just a number that you'll find in astronomy all over the place. I can actually go through that another night when we talk about, parallax and some of the other things we discover, because the number 206265 keeps popping up throughout astronomy. And it's important to understand where that came from. But for tonight, I just want you to use it. I don't want you to have to think about where it came from yet. We'll go there.
Okay.
We'll go there and figure out where, all about it and where it came from and everything.
Is it kind of like a magic number like pi?
Right
that
now,
keeps
we'll
showing
call
up
it a magic
everywhere?
number, yeah. And pi is not magic either. Pi is actually a ratio. It's a special ratio that occurs in nature with circles, always. So, it's pretty cool.
Okay.
Alright? Awesome. Alright, so, right now, I'm going to take us to that first star that is 145 arc seconds. We're going to go there now. Moving.
And Daryl's saying, your thumbnail held at arm's length is about half a degree.
That's right.
Because I remember reading something, I think it was when you could see like the first 5 planets all in alignment. I don't know if it was last year or the year before, and a lot of articles I was reading saying if you extend your arm out and make a fist, it was the distance between, I think it was 2 planets, but I can't remember. Was it the distance from the horizon to Mercury? It was something, but they calculated it just like that. It was making a clenched fist and having your arm at arm's length.
Yeah, no, there's...
So is that like a good measurement? Like...
Well, that is actually something that people will do. There is a little mnemonic you can use, a little trick that you can use, and that's one of them. And we do that a lot when we're trying to figure out heights, just off the top of our heads, just to give a rough measure, a rough degree, okay?
Is that what artists do when they're trying to measure things by their thumbnails?
Well, they hold out their thumbs, okay, and they do that because to them, their thumb, they know their thumb at arm's length is a certain, allows them to do a proportion. Mm-hmm. And so they translate that proportion to the canvas or to the paper. It's a common thing.
It's really cool.
Yeah. So here we are. By the way, I gotta go into full screen mode here because I wanna. Yeah, that's kind of hard. You'll have to tell me what's going on in chat because I went to full screen. All right, this double star that we're looking at right now is interesting because this star is 238 light years away. So, and its separation is 145 arc seconds. So now, for those of you that are out in chat, if you want to actually do this, all you have to do is take 145, and you should do this too, Amanda.
Yeah, I'm typing it in chat as you say it. Okay, 145.
145 times the distance to this star system, which is 238 light years. All of that whole quantity divided by the magic number 206265.
Okay, hold on.
206265.
Quantity. And divided by?
Yeah, all that divided by 206265.
Okay, so 145
times.
Let me get my calculator.
Oh yeah.
Oh,
don't worry, this will get quicker, and I'm not doing this because you have to. I'm just doing this because this is how you can actually take and do some astronomy, some real astronomy, right here, right now, live. Okay, so we'll figure this out. So 145
times that's arc seconds that these two stars are separated by.
Right.
Yes? Okay. Times 238 light years. That's how far it is from us.
Right.
Right? Okay, I got 3, 4, 5, 10.
Okay.
Then I divide it by
206,265.
6,265.
And what do you get?
is 0.167309044190725.
Okay. All right. Now that's in light years, and that doesn't really mean a whole lot. But let's put it in terms of something that does. Now multiply that by the number of astronomical units per light year. This way, the light years will cancel, and you'll be left with AU, and that is 63,241. Okay.
I don't know how to take that
63241 times that number you just did. Was it 0.1?
in. Okay. 10,580.791,263,66567. That's what I got.
Okay.
Uh-oh, where did I go wrong?
Say it again. What was the number?
10,580.79
The actual number is 10,583. So you did it right.
Oh.
You did it
Well,
right.
off by a little bit, but
No, but that's okay. That's because we're rounding up. We're rounding off. We didn't say it's 145.2. Okay, it's not. And it's 6,000 or 63,241.1. Okay, so if you did it all out, it would come out right. But this is the beginning. But you see how that works? It's really cool. Now, basically, all you have to do is keep that little equation handy. And just find the angular separation of a double star, multiply it times the distance to the double star, and then divide by that 206,265. And that's the answer in light years. Then you just multiply that answer by how many astronomical units are in a light year, and that can get you the astronomical units. And
wait a second. I have that written down. Was it 93?
93 million miles, yeah.
Yeah.
Now, if you want to convert
That's not the number you gave me, though. It was 63,241 or something, wasn't it?
Yeah, 93 million miles is the value of an astronomical unit. 63,241.1 is the number of astronomical units in a light year. So there's 63,000 of those 93 million mile segments in a light year. So that's how big space is. It's just huge. So you see.
Okay, but I mean.
Let's get a close up.
Okay, but you have to know all these numbers to plug them in. What if you don't know how far away it is from Earth, or?
Well, then you do what astronomers did for centuries, okay, and still do. You do studies to figure out how far the stars are away from you. You look for things like parallax. If they're under 1,000 light years away, then you can do parallax, where the Earth on either side of its orbit can get you measurements of the star system against farther background stars, and that gives you a distance to those stars in the foreground, and that's one way. If it's farther than 1,000 light years, then we got to use another trick. We have to look for things called Cepheid variables, and these are variable stars that have a relationship of their brightness to their period of the variable stars that vary in brightness. But the period of that brightness fluctuation, the period of that luminosity fluctuation, is well known to go with their luminosity, that is their brightness. So if the period is 3 days, if the period's 3 days, then it means that the star is going to be this luminous. Now, if you get the apparent magnitude of that star in the sky, you can then figure out what's called its absolute magnitude. I know I'm going way down a path here that we don't have to, but the bottom line is that you can then take those stars that are called Cepheid variables, and you can find the distance to them just by looking at how much they vary in brightness, what the period of variation is, 2 days, 4 days, 6 months. And then you take that number, and then you work out what the star's luminosity is and how bright it is as you see it. And that apparent brightness, that apparent magnitude of the star, is something that we can use on a well-known relation called the period luminosity relationship. And all you do is plug in the star. You look at there's something you don't know. You don't know what's called the absolute magnitude, which is the magnitude that a star would have if it was 32.6 light years away. It's a standard that we just came up with in astronomy. And if you know how bright the star would be at 32.6 light years, and you see its apparent brightness in the sky, then you have something called the distance modulus, and you can then use that to calculate the distance, because that's the only other variable on the other side of the equation. It's like, the absolute magnitude minus the apparent magnitude, the apparent magnitude minus the absolute magnitude, I believe, and then that equals, there's a logarithm there. It's like 5 log of the distance and so forth. There's simplifications to the formula, but the distance modulus equation is something that we've used to get the distances to stars, and it works well, and the data is pretty cut and dry. Now, on this star that we're looking at, by the way, this double star, you're looking at stars now that are separated by 10,000, 580 astronomical units, and the double star, I didn't even tell you what it was. That is remiss of me. I should have told you right up front. We're actually looking.
I was good to ask. Yeah.
Yeah, it's a star called 17 Coma Berenices. We're in the constellation Coma Berenices. All right, and that's Berenice's hair. That's what it's meant to be. And the star is a 5th magnitude star, and it's a variable star, not a Cepheid variable, but it is a variable double star. And the interesting thing about this star is that the whiter one is actually a subgiant. It's just below giant stage, and it's actually an A1 star. So not an A0 like Vega, but an A1, just a little bit later in spectral class. And its surface temperature is around 10,000 degrees, a little bit less. It's actually it's 1.6 times hotter than the sun, basically, if you look at it that way. But it's 2.5 times the diameter of the sun, so it's actually much bigger than the sun. It's more than twice as big as the sun. Yet its temperature is about that of the sun, just a little bit higher than the sun. So it's a big star, all right? And its overall intrinsic brightness, that thing we call luminosity, is literally 42 times the brightness of the sun. And it's 2.7 times the mass of the sun. So, and that's the star on the left that we're looking at. Now, these stars, as I said, these are actually locked in an orbit, and I think that if I don't miss my guess, this star will vary in brightness over a period of 5.1 days. Actually, I'm seeing that here. It's a 5.1 day period, meaning that you could literally measure the star's brightness over a week, and you'll see it change. And it's rhythmic. It's right on. It keeps doing it. It's pretty cool. That's really cool. I like this. So this is the first visit for the night. We're going to this guy here, and I think that we're pretty much done here, unless anyone has any commercials. Commercials. I don't have any commercials. I don't know where I was going with that. Sorry. Questions is what I meant. Sorry.
Well, it's funny. Daryl's already filling me in on because when you said 32.6,
yeah,
I don't know, when you said that number and you're like that because that's just the number we made up. I was thinking you can't just make up numbers, why? But again, math is a totally different. I'll work on that.
Yeah,
I'll work on that as we go.
It's an astronomical
constant.
It's an astronomical constant. It's actually 10 parsecs. Okay. And
apparently, yes. Daryl told me that.
Yeah, okay. A parsec is 3.26 light years, and so that's why I said 32.6, because it's 10 of those parsecs.
And Ian said it the other way. That's what I love about chat. Not a lot of questions are coming in because I think everyone's just listening, just enjoying the view and listening to what you're saying because it's like they know, they can hear my voice when it starts to fall apart and.
No, it's just maybe you're asking all the questions for them.
Hopefully I'm asking them for someone, maybe that doesn't have the chance to ask these in live time or whatever, but,
That's okay. That is
um,
okay.
let's see. Light year, parsecs, paraxle,
Parallax.
parallax, arc second. Okay.
Yeah.
Sure.
Yeah.
Yeah. Parsec is 3.26 light years, the distance at 1 AU, 93 million miles, 1 Earth-Sun orbit radius, would subtend 1 arc second.
As seen from 3.26 light years.
Yeah, so, I mean...
It's the distance a star would have to be so that it would actually move 1 arc second, as seen from our Earth orbit, which
Okay.
has a radius of 93 million miles. Obviously, it's a diameter of 186 million miles.
Okay, so now,
right?
And I hope that I'm following this. Okay, so these stars orbit each other. Yes?
Yes, they do.
Okay, and so if we watch this for 5.1 days.
No, you're confusing it.
Oh.
Yeah, doesn't take 5.1 days for the stars to go around each other. That means the stars have to be going at way faster than light speed. That's the time over which the main star there on the left dims slightly.
But I thought we saw the dimming when the star would be passing by it. Like, I thought that's what the whole Tabby star was about. That something was passing in front of it, and they thought it was something else, and then when they figured...
Well, we still don't know what Tabby star is dimming from, and what we're seeing here, a variable star is a star that varies in its brightness. It gets dimmer, then it gets brighter. Tabby star is not getting brighter. Tabby star is perpetually dimming for over 100 years now. So that's a very different situation. That's something that has been unseen in the astronomical world. It's not something that's normal. It's not a normal thing. Do you understand?
Yeah, kinda. Well, I mean, as much as I can, but
okay.
Again, I'll go back. I'm trying to take notes, and I'm trying to...
That's okay.
See, it's just I have a feeling I'm gonna ask a question that's gonna, like, veer us off on such a different topic and get everyone confused, so I'm just gonna jot things down and,
Nonsense.
listen.
Nonsense. You won't be doing that. Okay, let's see.
But I'm writing down, actually, kind of what to look for, like, making notes for myself on what to look for to get that formula, so hopefully by maybe the third one, if you give me the numbers, I'll figure out how to do it.
Sure.
And I'll know what to... Well, if I know what to look for, then I can probably find charts to... You know, if I wanted to find a double star, I could find how many arc seconds or minutes arc seconds that it was apart, and how many AUs from Earth it was.
Yep.
No.
You could.
Oh. I don't know. Okay, next one. I'm getting this. I'm getting this.
You'll get there. All right, now we're going to go to another star called Kappa Bootis. It's Kappa. It's the star in the constellation. I'll tell you in a second. Okay. Okay, this is the star. Jericho's, it just went away and it'll come back. This is a star that went, is in the constellation Bootis, the sheepherder, and let me just bring back this. Hang on. Is that where we are? I think that's where we are. 1 second. I'm in a little bit of a wire mix-up here. I gotta move around to get out of the wire range here. All right, what do we got? Okay, let's see. Yeah, there it is. Okay, now here's a different one for you. Okay, this star, Kappa Bootis, is actually very interesting because this star, these two components are really fascinating because they are separated by not 145 arc seconds, but a lot less, aren't they? Okay.
Yeah, it looks like just this tiny little sliver. Oh, it's getting bigger now. Okay, hold on.
Yeah.
Still very,
Well,
very small.
it's there. It's a little bigger now. So you can actually see when you look at this star that the separation is much closer. Now I'll tell you something about the stars. These are two stars that basically sum together to give us a star that is a yellow-white A8 type star. Okay, A8. So in the OBAFGKM scale, it's an A8. Vega's an A0. We're a G2. So you can see that star on the left has got a little bit of blue in it, and then but it's yellow-white because of its component. Now, this is called Kappa in the Greek alphabet. Kappa, and it is 100 and let me get it right here. I just want to make sure I get it. I had it written down here. Just want to make sure I give it to you correctly, because when you do the calculation, I want you to get it right. All right, this pair is 163 light years away. All right, and the separation is 13.5 arc seconds. So let's see who can get the answer quicker.
Hold on, I don't even know how to clear my calculator. Hold on, what is the distance between the two stars in arc seconds?
Arc seconds is 13.5 arc seconds.
13.5.
And the distance.
And how far away is it from us?
163 light years. And while you're doing that, I'll tell you the second star. Okay,
where's the back button? Oh no.
The second star, that smaller one that you see there, that's actually an F-type star. Okay, so its spectral class is F. So OBAF, just before G. It's actually an F1. And its magnitude, its brightness is 6.58. And when I mention magnitude, I always mean apparent magnitude, all right, which is the magnitude that it just appears to us as we see it in the sky. It's not the absolute magnitude, which is the magnitude it would be if we brought it to 10 parsecs away. That's what apparent versus absolute magnitude is. And then one night we'll get into why we do that and have an absolute magnitude scale. Why don't we just keep the apparent magnitude? We'll get there. All right, so 13.
Okay, wait. I have the number in decimal point, but I forget what I'm supposed to do now.
That's okay. 13.5 arc seconds at 163 light years away.
Mm-hmm.
You multiply those two together, and then you divide it by
206,265.
That's correct. And what do you get?
And I got 0.01. No, sorry, 0.01066. But I forget what to do now to bring it back to a normal number.
Now that's in light years, remember, because we did a distance in light years.
Okay. Oh, hold on. This 0.010. This is in light years.
Yes, it is.
Okay.
And it makes sense that it's a smaller number than the last one, doesn't it? Because these stars are closer together at about the same distance. That's why I brought this double up. So now take that number, and now you want to cancel out light years. You want to figure out how many astronomical units these stars are from each other. So to do that, all you have to do is multiply that 0.010 by 63,241. And that gives you the astronomical units between these two stars.
Okay. Is it always going to be 63,241?
That's the number of astronomical units in a light year. So the answer is yes, it will always be 63,241. So has anybody in chat done this already, or are they just sort of like going, why are we?
No, I don't know. I think they'll have their fingers crossed that I get this answer, but
you're like thinking, I don't want to be to class. I don't want to do work. I get it. Now, since I'm not doing the calculation, I'm just waiting for you to do it, BB. I'm just curious what you come up with.
674.67.
674 astronomical units, basically. 675 astronomical units.
Mm-hmm.
Okay.
How far off was I?
Well, I said I don't know. I didn't do it. But I could. I mean, I could actually do it.
Oh, I thought you had the answer there. And
No, see, that's the whole thing. We're calculating these answers dynamically, okay? So, all right, if we do this now, it's really not hard. So I couldn't do it in my head because I was doing other things here, so I apologize for that. So basically, it's 163 times, as we said, the 13.5, right? And that equals the 2200.5 divided by 206,265. That's what you said, 0.010. Now we multiply that times 63,241.1, and the answer is 674.67 astronomical units between these two stars.
That's exactly what I got, yay.
Yeah, 674 astronomical units. Now, here's what's interesting. If you take, that's 674 times the distance of our Earth to the Sun. All right? And, there's no planets that are 674 AU from us. If our solar system was there around that left-hand star, it would fit right around that left-hand star, and that other star on the outside would still be in our solar system and the far reaches, but it wouldn't be anything but a bright star in our night sky. You see? That's what's interesting about this, if you put it in terms of all that. So that's what's really cool. So this is an A star on the left and an F star on the right. And they're just gems, aren't they? They're beautiful. And I realize I've got the magnified view here, so you're not seeing these in any other way but digitally like this. But if I go back to what they normally are, okay, then they're this is how big they look to the eye, and that is really when you look at this is in the prime focus of a telescope. It's like really tiny, but I think what I want to do, just because it'll be helpful to you, is I'm going to take a very short exposure of these, okay, and it's meant to be a short exposure because I want to try and see what we get when we zoom in on this. Alright, so there you can actually see on the screen, you can actually see that the intrinsic brightness of that A star versus the F pretty clearly. It's pretty cool. I'm very happy with this. This is looking good. I just solved the headphone issue. I let the headphone go right around the pier. Okay, cool. So that's really interesting. I like that. That's probably a favorite star, favorite double. Now let's go.
When you have it in this shot, I don't know if you've done anything since, but I'm looking at right now. The one on the bottom right looks so much smaller and dimmer in comparison. Like on that particular shot, it wasn't as noticeable to me on the other angle we were looking at.
Yeah, that's true. It is. And then when you zoom in on it, okay, you actually see that it's actually much less luminous, and they're right next to each other. Well, 670 astronomical units apart from each other, but still. So do you folks, do you think that's cool? Figuring out the distance between the stars. If you do, let me know. It's something we can do occasionally. I'm not going to do this as like a lesson every single time, but I'll just tell you if I know the answer, which is kind of cool. But I want you to understand how to do it, so that you have it kind of under your belt. You understand. Hopefully.
I like the image I'm looking at now. They look like so
little gems.
Yeah.
And the thing is, we're aware of planets going around stars, but when we see stars going around stars, and then planets circling those, that's even more incredible. I have to go to Devil's Tower, Wyoming in September to do a talk at a conference, and I'm going to do a talk on exoplanets. And we're actually going to have exoplanet models there with their stars, and they'll be lit up. And those are going to show folks in a model form what we're talking about. And it's going to be incredible to have these. I want to have one double star system with like I might do Alpha Centauri with component A and B of Alpha Centauri with Proxima way on the outside with a little planet circling it. And it's going to be a physical model. There's going to be physical spheres that are lit from inside to show people these actual models, and that'll be on stage while I'm doing the demo, while I'm doing the talk. And as I motion to it, it's going to turn on. So we got this some additional technology here that we're going to use to actually light it up, that's and now Jude, who's out maybe in the chat listening, is going to go, oh gosh, no, I don't believe you said a triple star. Yes, I want to use Alpha Centauri, Jude, and it's going to be 2 stars of the same brightness, A and B, and then the red star Proxima that circles both of them. And we're going to be using that and talk about Proxima B, that exoplanet around the nearest star system to us. So let's talk about Alpha Centauri for just 1 second. Exactly, I've said this before. It's a triple star system. A and B components are about like the sun, and Proxima is a little red dwarf, circling both stars, orbiting those stars. And Proxima is a beautiful little dwarf. It's relatively dim. Can't see it with your eye. You need a telescope. However, it is gravitationally bound to A and B, and we found a planet circling Proxima, and it's called B. We don't call it A, and it's a little b. All right. Really, really interesting that the nearest star system to us has that. And incidentally, when I say nearest star system, Proxima right now in its orbit around A and B is the closest star of the 3 to us. So Proxima is the closest star to us. All right. And it's part of the Alpha Centauri star system. Well, look at it. I tap on the telescope and we get a little dance going on there. We actually do this in astronomy. We tap on our mounts like on the telescope like I just did there, and we time how long it takes for the vibration to go away. And that actually gives us some valuable metrics on the stability and quality of our stand. I can also bang on the observatory floor and stuff, and as you can see, when you hear me banging, and virtually nothing's happening. The star is staying fairly intact, and the only reason it's moving a little is because the wires going under the pier actually contact part of the floor covering, which is a rubber matting, and it makes the slightest of vibrations, but notice how quick it deadens and goes away. Very important when you're taking pictures. So on to Kai Buddhist, which is right nearby, and we're moving.
I love that name, Kai.
Yeah. I love stars, what can I tell you?
No, but I mean, again, like, astronomy, like, I mean, yes, it's hard. We're talking about, like, crazy, crazy numbers and distances that you can't really comprehend, but, like,
yeah.
Like, putting your arms outreached and using your thumbnail or using a clenched fist and, like, physically tapping on the telescope and stuff, like, that's just, like, logical ways of estimating, and
that's right.
But yet it turns out to be such an accurate form of measuring things. Like, it's very, very fascinating, and
it is indeed.
I had no idea when you put your hand in front of the telescope,
yeah,
and it only got darker. We couldn't actually see your hand.
Right.
I had no idea. I mean, I'm just blown away by the stars and planets and everything we're looking at. I never really, don't really think about the telescope on its own, and I know a lot of people are. They're asking very specific questions about the cameras you use, the telescopes, and
yep.
First things first,
Yeah.
But yeah, it's It is. It's very logical, and I can see, you know, like Galileo using things like that, and it's still the standard we go by now. Well, more accurate now, but you know what I mean.
That's actually a very good point, Amanda. And to add to what you said, you know, and what the folks have to understand is that I'm coming to astronomy from the point of view of being a guy who's been into astronomy, has a degree in astronomy, has worked in astronomy pretty much my entire life. And then Amanda comes along, and she's from a perspective of never having been into astronomy except for the wonderment and the awe of seeing these beautiful things in the sky, like the thing we're seeing now, okay? And yet, when she asks a question, you know, I hear in her voice, I hear the innocence of not knowing the answer, okay? But I also hear the bravery of her asking a question that she knows to ask anybody else, she could end up getting embarrassed by it or something. But again, I've told you this before, there's no stupid question. And her observation right now was actually pretty cool. She said, you know, maybe Galileo would actually use the same kind of metrics that we're seeing here, you know, that we talk about. And he most certainly did, you know, no doubt in my mind. And by the way, there was a plane that was about to cross right in front of what we're looking at, but it's just out of our field. Anyway, that was good, Amanda. I wanted to just, you know, thank you for offering that.
Well, like you said, I could ask a lot of people, and they'd be like, "Oh my God, is she like the world's best actress? Like, is she really that dumb?" Because if not, like, it's hard to believe. Like, you know, I don't know. Like, it's not knowing. You got to start somewhere, and you never once made me feel bad about anything I've asked, no matter how many times I've asked you to repeat it over and over again. And
oh yes, and that's fine. You know, I want people to ask, because if you're asking, then certainly someone else wants to, and that's the point. Now, let's dive in here to Chi Buddhist. Chi is spelled X-I, okay, and it's a double star system. This one's 21.8 light years away, okay, and if you notice, all right, these stars are very close together, aren't they? They look very close. Now, at 21.9 light years away, these stars only have a separation of 5.4 arc seconds. So those of you in the chat, you can go to town here and figure out how far they are apart in astronomical units. Okay?
Hold on, I'm working it too.
Then you can. 5.4 arc seconds and 21.9 light years. Okay? 5.4 arc seconds apart and 21.9 light years away. And while you're doing it, I'll tell you about these. Now, here's the interesting thing. Their orbit is, I don't want to tell you the numbers because I don't want to mess you up if for those of you in the chat listening, but their orbit is just over 150 years that they go around each other. So people in the past would have been able to see these stars do a complete orbit without any problem. It would just take some time. And the distance that they are apart can be anywhere from 2.5 arc seconds to 7 arc seconds. And that depends on where they are in their orbit. Now remember, their orbit's not right on 90 degrees to us, or flat on to us, or edge on to us. It's some oblique angle. And that's what causes them to, the stars to be differently apart from us as we look at them at different times. Now, so you should be pretty much done with that calculation, so I can tell you the orbit of the stars is 151.6 years that it takes the stars to go around each other. And what?
That's not what I got.
No, that's the orbit of the stars. That's
oh, okay.
That's how long it takes them to go around each other. Okay. No. So, what did you work out? First of all, did anybody in the chat come up with a number yet?
No, I don't know if they are trying or not, though.
Okay.
Or maybe, I don't know, maybe they're just waiting for my answer first because they don't want me to just cheat off them.
Well, again, 5.4 arc seconds at 21.9 light years away, and then you multiply that number at the end. So what'd you get?
I got 9.06.
9.06.
Well, because, yeah, I took 5.4, multiplied it by 21.9,
Yeah.
divided by 206. Oh, I lost the number. 206,265.
Okay.
And then I multiplied it by 241.
All right. And what?
Yes?
And what you get?
And
For
I got
answer?
9.06.
9.06.
I did something wrong. Did I do the steps right and I just maybe hit the wrong button or something? Hold on.
Yeah, I mean the
5.4 times 21.9. I could have easily hit the
no,
wrong
that's
button.
okay. I'm
Divided
I'm
by
just
206.
sitting back waiting. Don't worry.
65.
Don't worry about me.
Okay, and then I'm multiplying, right?
Yes.
Okay, yeah. Okay, well right now I got 5.7. So now I'm multiplying 6, 3, 2, 4, 1. Okay. I must have hit something wrong then. Now I'm getting 36.25. Does that sound closer?
Yeah, actually it does.
Okay. I must have switched numbers or something. Okay.
That's okay. The answer actually, the typical separation, and again, like I told you, it depends where they are in their orbit and when you do this, okay? But, you know, they have a separation that's anywhere between, well, okay, right now you should come up with something in the 30s, okay? Like 33.5 AU is probably valuable, is a valid number. And basically that's that's just a little farther than Neptune from our sun. And that's what you're seeing here, is two stars where if that was our sun on the left, that would be where Neptune is on the right. Okay, so that's pretty incredible. So if you're in that star system, just imagine a second bright star in the sky where Neptune is in our sky, and you go, wow. I mean, that's what it'd be like to be living in a stellar system around those stars. Pretty cool, huh?
That's crazy.
Oh yeah, yeah. And these are both normal main sequence stars. That means they're fusing hydrogen to helium in their cores. Uh, and you know, one is a G8 star, so it's just a little later in spectral class than our sun, which is a G2. Okay, and you know the other one, the other one I'm looking for. That one I had that here somewhere. Where is it? Oh, the other one is actually it's slightly fainter. The fainter one that's on the upper right there, that's actually a K4 or K5. So that's just before M. You know, M is like after K9. Dog. Woof. After K9 comes M0, right? So, but these are K4s to K5 or so. That one on the right. So we have two stars that they actually combine to give us a combined light, which is kind of cool. And that combined light will end up kind of looking like that brighter star on the left, which is the G star. So it's pretty cool. All right.
Is that as close as you can get it on the screen right now? Can you zoom in anymore? Or?
Actually, no, I think that's as close as I can get. Hold on. Yeah, see, that's far away. See, it looks like one star there. Then.
Well, I can see
secondary.
the smaller one kind of to the top right, but
yeah.
The bigger one not in front, but the bigger one to the left. If that was our sun, the smaller one would be about Neptune, Pluto away.
It would be Neptune's.
That was us.
Just over Neptune's distance, yeah.
See, that is mind blowing.
Yeah, that's actually putting it into perspective you can understand. Kinda.
So yeah, well, kind of exactly, but okay, well, how long does Elon Musk predict it would take to get to Neptune? His Mars orbiter, he thinks he has to rename because he thinks it can actually go a lot further than Mars. I know Neptune's way down there, but I mean.
Yeah, Neptune's like 30 AUs out, you know, and these two stars are separated by, you know, 33 or 35 or so, depending, well, or more or less, depending on when you do this calculation and with what values. Yeah.
That is, again, it's good. Little things like that. Really, I mean, again, it's still hard to fathom, but that looks like such a little space in between them.
I know, and that's because we're seeing stars that are bloating their image because of our atmosphere. You know, if we saw these by the Hubble in true form, we'd actually see that the stars are a lot smaller, but we still wouldn't be able to see them as disks. You know, as the disks they are, and it's still quite a bit smaller. You know, thousands of times smaller, as a matter of fact. So when you look at this, keep in mind, and here's another fact I'm springing on you now that you don't know. This star system, that left-hand G-type star, might actually have habitable planets around it. Ta-da! This is one of the exoplanet stars that I promised to show you tonight. I'm sneaking them in little by little.
And this is Kai Buddha?
Kai Bootis, Bootis. The constellation is Bootis, you know, Bootes, the sheep herder, you know. And this is Chi, Xi. And now there were certain anomalies in the star's motion because when they have orbits about each other, those orbits can be altered by anything else that's orbiting around them. Now, if we have a Neptune distance star out there, then certainly they're gravitationally bound. The star that's the distance of Neptune away probably doesn't have as much of an influence on the planets around the other component as the other component does. And that's probably where they're centered, and that's what they think they found. And based on these anomalous motions, they think that there's actually planets around that bigger, brighter star. And if that's the case, then we're talking about an incredible opportunity here. An incredible opportunity. And I would think that it's going to be one of those stars that we're going to eventually want to keep on our short list because, again, it's not far away, is it?
Is it 36 AU away?
Well,
no.
From them, but it's 22 light years from us. And if we get an Alcubierre drive at some point, then we're going to be able to warp to it in a matter of a couple of months.
Wow.
Yeah, and we'd want to go. Wouldn't we want to go? I'd want to go. So
would you though? I mean, I know that it gets asked a lot of you, especially, but you would go?
Well, no, I wouldn't be able to do the SkyTour anymore if I did that. So honestly, I don't know if I would.
Take it on the road. Take it into space.
Yeah, can you imagine the same view night after night? Yeah, I don't think so. I'm okay with it. I'm okay with sticking around here. I still want to see a nice dark sky in Arizona first, and that's going to take my breath away, and that's going to keep me there for some time, I can tell you that.
Mm-hmm.
Yeah.
SP said they'd go.
There you go. Incidentally, this particular star, because the left-hand star is kind of like our sun, as I talked about, then that's why they suspect that with a motion like that, that it's possible that planets around that star might actually be able to harbor life if they're in the habitable zone. So they're working on it. They're trying to figure out where the planets are. It's not guaranteed, but it's possible.
Is there any way you can raise the volume on your mic?
I can just talk louder. Okay.
Like move it up your shirt anywhere, or
if I do this, then if I raise the volume on my mic, then I'm going to be messing with that possibility of creating your echo again.
Yeah. Okay.
But I just ask people until I get the wireless in another couple of days. And like I said, it's going to sound like this once I get it.
Yeah.
Yeah, that'll be better. I grant you, and I just teased you with that, and I apologize. But unfortunately, for now, this is what we got. But it'll change. Don't worry.
Oh yeah. I'm just happy the echo is gone. And I know it was because of the streaming, but that delay, oh, that really put a wrench into the works.
No, the streaming, that's not what it was, because it didn't even happen within OBS. The delay was caused by Skype and by my microphone settings within Skype that you were coming in on. Apparently, because I had my microphone up too loud, people could hear me, but they could also hear all the background noise going on in here, and it was actually very disturbing to a lot of people. Now you hear more of my voice with the music softly in the background, and you don't hear the cars going by, which have been, I mean, you do, only the loud ones. But most of the cars that were going by from the shunted construction traffic, you didn't hear, because you can't hear them now, and they're going by, and it's because we've actually toned this down. I toned down the sensitivity. Now it does remove a little of my volume, but as I said, that's going to change shortly, when I get this up. Any questions on this star, by the way? This pair of stars?
Well, there is a question from Daryl, maybe not particularly on this one, but he would like you to talk about the stars' distance to each other versus their orbital period. Do their masses have an effect? I assume this would get into Kepler's laws.
You are correct on all three accounts. The star's mass does have an effect. That determines the orbital velocity required for the stars to stay in orbit around each other. And you mentioned Kepler's laws. Kepler's laws do come into play here, all right? And when we look at the orbits of the stars going around each other, they will adhere to Kepler's laws. And as far as the planets going around the star on the left, the main component, they will also adhere to Kepler's laws. Now you might wonder, well, what happens if planets are a little farther out? Could they possibly have this really weird figure-8 orbit where they go around the right-hand star once and then the left-hand star next or something? Because what if the two stars orbited each other at a slight elliptical way, so that what's called the eccentricity or the ovalness of the orbit is not 0, which is a circle, but 0.3 or something like that, where it's slightly eccentric. If it was like that, you might want to know whether a star could capture the planet for one orbit, and then as it changes its orbit, the planet goes back to orbiting the other star. Well, to simulate stuff like that, I highly recommend that you get Universe Sandbox 2. It's an application available on Steam, or available, I think, from their site. And Universe Sandbox 2 is a great simulator of the physics, and you can do collisions of planets. You can send asteroids into Earth. You can send asteroids into the moon, watch the moon's orbit change over time, and look at the impact, say, of an asteroid on the moon and what it does to Earth long term. We're going to use Universe Sandbox 2 as a cloudy weather streaming tool. And we're going to be doing some really cool scenarios, which I'm developing. And I have TRAPPIST-1 in here already, and we're going to be able to simulate that entire system, TRAPPIST-1, complete with the habitable zones visible, so you can see where the planets are that are habitable. It's really cool, but it's digital simulation. It's not real like this. This is real astronomy we're looking at right here. So hopefully you'll like that.
Well, I was going to ask, I think a few people in here have used that Universe Sandbox app, and you were showing me a few scenarios, I don't know, a week or so ago. Don't things like that give you nightmares, though? Because it like counts down. It's like, okay, here's the 0 hour where the impact actually hits, and then like you're watching Earth just get destroyed over like in real-time hours and stuff, like. Well, and some of these are possible situations, or could be in the future. Like, doesn't that terrify you?
It does, and you know what? There's nothing like a good scare to not just get your blood flowing, but to get your technology going. And if someday we are going to be defending our planet against an asteroid strike, then you have to look at what could possibly happen to our planet. You have to look at what happens if something the size of the moon were to strike our planet. Now, that's not likely, but it is a scenario that you would want to take into account and say, well, how would I move something the size of the moon out of the way? Currently, there's no way. We have no way to do that. None whatsoever. So, that's unfortunately basically what we have to deal with. We don't have any way to actually do this right now. Maybe someday we will, you know.
What was the latest? I forget. I don't know if it was Elon Musk. I forget. But weren't they talking about like sending a rocket to potential asteroids to veer them off course or something? Was that what they were trying to do, or not just blow them up in space because that could make the situation worse?
Yeah, very good.
Were they trying to like control them? Yeah.
Actually, there's a number of theories for controlling asteroids. One was to soft land on one of these asteroids with a nuclear thruster and just turn it on, you know, and just have it go for like 4 years. And it would slowly nudge the asteroid into a different orbit. Now that would work, but we'd have to see the thing coming. We'd have to have time. And that's typically what astronomy isn't good at yet, is getting to things in time. We always hear after the fact, a small asteroid passed between the Earth and Moon Sunday. Wait, well, what? Sunday? Yes, it was the size of a house, and if it hit the Earth, it could have potentially gotten down to the planet and, you know, caused far more damage than the Chelyabinsk meteor a couple years ago. You know, it blew out windows everywhere. 1,500 people were injured, and that was just a small meteor. That was only one that was about 500 tons. You know, so but that's still a heavy beastie to come down, and it made it through the atmosphere and blew up 80 miles up. You know, boom, or no, 14 miles up, and it actually sent shockwaves through the atmosphere that destroyed a lot of property and building stuff. So collapsed the roof too in one factory. So that kind of thing is something we want to avoid. But we don't see them coming. We're not going to ever see them coming, and it's not yet. We will.
Well, see, I mean, it's a good theory. I mean, if we could get it into practice, yeah, I think it would work. But you said someone that was working on Philae, and that took 10 years of careful timing and planning to land on something moving so far away, right? So
yes,
we don't, by the time we see it, if we're so bad at predicting, we say something after the fact, do we have 10 years to, like how, I mean, it would have to be pretty instant the second we saw it, we launch,
Well, we'd have to know it was there. We'd have to, we'd have to have a database and have an ongoing Skywatch. Okay, we'd have to have an ongoing Skywatch that would help us figure these things out. Because right now we don't know. We don't know, and that is unsettling. I grant you. But you also have to understand that we actually don't have asteroids heading for us right now that we know of. The biggest threats to us are going to be the Earth-crossing asteroids. Those are the ones that cross the Earth's orbit. Now, that doesn't mean that the asteroids out in the asteroid belt are coming zinging in through the inner solar system all the time. That does not happen. They're happy out in their orbits and they stay there just fine. We do have perturbed objects. That doesn't mean they're angry. Okay? It just means that they get moved out of their orbit by a comet that passes by or whatever, and it starts a dance that gets them to eventually take up a new orbit where they either go and cross and go into the sun, or they head around the Earth and head out to space. And those are the asteroids that are actually something we have to worry about. And those are actually in our orbit. Those are actually in our orbit. They're 60 degrees ahead of us and 60 degrees behind us. And that's something That's something we have to be concerned with. These asteroids can and do get dislodged from their orbits and then end up finding their way. And it's very likely that the one that struck the Yucatan, off the Yucatan Peninsula 65 million years ago, the one that one that killed the dinosaurs over time, it's very possible that one was one of these Earth crossers that got launched out of its orbit by an interaction with a passing comet or some such thing. So we got that. You got that as a possibility.
Is asteroid Apophis coming close to Earth in 2029?
That's one of the near-Earth asteroids, right? That's coming this way. Wow. I couldn't show it to you in time, but I just had an Iridium satellite flare go off over here, and it was brighter than Jupiter in the sky, so much brighter that I bet I could have seen my shadow by it. It was really, really bright.
Wow.
Now, I don't know about Apophis, but let me just mention quick about these Iridiums. If you get a satellite program, one that I use all the time is called GoSat-Watch. I know it sounds like Run Spot Run, but it's GoSat-Watch. And it's on the iPhone. It might be an Android as well. But GoSat-Watch allows you to see when satellites are going to be over and what they're going to do. But you have these others that are really interesting called Iridium satellites. What's an Iridium? An Iridium satellite is a satellite that's actually covered with very bright panels. And as the satellite goes overhead, the glare, the reflecting sunlight that comes off of it while it's up in orbit, sometimes is reflected down to the ground along a specific path. Well, those specific paths are called flares, and a flare path. And that specific path is well known and predictable. So when we see it, we actually can predict when we're going to see it. We can actually predict where it's going to be. And a prediction came up. You might have heard that little, noise go off on my iPad here that I use to drive the telescope around. And it said that coming up is this flare. And I didn't know how accurate it was, but I kept looking to see when it was. And I looked up, and there it was. It came in, and then it lasted about 3 seconds, and then it was gone. But it came in, got very, very bright, and then faded away. Those are called Iridium flares, and they're very predictable. And I had a Mars party here one night, and the Mars party, I had all these telescopes set up. This was before the observatory was even set up. And I had this telescope out and operational, and it was up on a tripod, and people were looking through it, and we had 2 or 3 other scopes here. And we actually set this up, and everybody was having a great time, and then it was time to go. They packed up and they left, and I was packing up my scope last. I was waving to the last guy to leave. And as I looked up, I had 2 Iridium satellites overhead that were going into flare mode at the same time. They were like 2 bright eyes up in the sky, and I can't believe that they left too soon to see him. And I was the only one to see him. I just stared at him and said, I'm the only one that gets to see this right now. This is kind of special. And I shook my head and looked down, and I could see a double shadow. I could see my shadow from both satellites. It was absolutely astonishing.
Oh my god.
And that was from sunlight reflecting off the panels of these satellites. So that's cool stuff. So
that's crazy.
Now they call them Iridium flashers, okay, but Iridium flare is what they do. They flare. They kind of get higher and then lower. We see stars do that too when they go nova, not supernova. When a star goes nova, when a star ends its life, like for instance, these pair here, if that star on the right became a white dwarf, and if for some reason it got nudged closer to the star and started circling the star in a close orbit, then it might pull material off of that left-hand star and pull it onto its own white dwarf surface if it became a white dwarf. And as it did so, the special material that's in the white dwarf would eventually get overwhelmed, and it would slough this stuff off in a fairly violent little mini explosion called a nova. And it would just puff the stuff off, like poof, off it would go. And then it would just continue to, you know, accrete material from the big star again until, you know, the big star finally went into its end phases. And then it probably ended up with these two stars to be two white dwarfs circling each other forever in the end. But that nova would cause the star to get very, very bright for a period of hours and days. You know, not many days, maybe a day, and then it would get dim again. Supernovas, on the other hand, that's when the star obliterates itself. All right, not just a white dwarf getting indigestion, okay, like this. Okay, that would be indigestion of a white dwarf, but a regular nova. But the supernova is when the star actually obliterates itself after it finishes its, you know, nuclear fusion processes, and there's none left. The star collapses because it has its outward radiation pressure of its activities that hold it up, basically, because it's always trying to collapse with its own gravity. But if that went away suddenly, like it does with these larger stars, then they collapse on themselves. And the only place they can go is on that immutable, unmovable core of material that was created in the center. And once it does that, it just explodes back outward again. And you've heard it called perhaps a rebound effect. Not necessarily a rebound, actually. There's more to it than that. But the fact is, you can think of it as a rebound where it has no place to go, so it bounces back outward, and it takes all of the rest of the star with it, leaving behind a neutron star or a pulsar. And these cores, these typically rapidly rotating stellar cores left behind, are the only testament to what the once massive star was. And the filamentary structure of the nebula that's expanding around that star, the gaseous clouds of elements, literally periodic table elements that are expanding around that star, are the only other testament and evidence to indicate what happened. In the winter, when winter comes along, I don't want to hear about it, but when it does, we're going to look at Messier 1, the very first Messier object, and it was called the Crab Nebula. It's actually really beautiful in this camera. I've done it a number of times, and you'll like it. And it's actually, Messier 1 is actually a supernova remnant. And when the moon disappears soon, we're going to image the Veil supernova remnant up in Cygnus, which is going to be overhead by the time we're ready to image it. And that's the best time to do so. And you'll actually see the filamentary structure of the Veil Nebula. Really, really, really nice. And in special color, too. It's a lot of different colors. It has reds and it has blues. It's really, really cool. And the reds and the blues correspond to different chemistry, and we'll talk about those at the time. Little by little, I'll ease you into astronomy. I'll make you love astronomy. And then you can walk up to people and say, hey, do you astronomy? And they'll go, what? And you say, do you astronomy? And they'll look at you funny, and you can say, I didn't think so, and just walk away, proud, It's the thing. I astronomy, do you astronomy? Yeah, okay. I also want to take this moment to tell you about a television show that I'm a member of, that our second season comes out. We're going to start taping in July, or end of July, or early August, I believe. It's called the Connecticut UFO Show, and I'm one of the hosts, and we have two other people on board. We have Mike Panicello, who's the state director of MUFON for Connecticut. We have Warren Fentress, who's an investigator, an FI, a field investigator for MUFON, and myself. And I have a segment on there that's called The Science of It All, and I explain the science, like I am now to you, about the science of the universe and everything, or the science of potential propulsion that UFOs are using. Don't forget, I might be a science guy, but I'm also one of these science guys that does believe in these possibilities and the possible extraterrestrial presence here on Earth. And now, why? I do because of everything I've been teaching you and showing you. I do because I believe that we have a lot of habitable stars in this galaxy alone. We have a lot of planets that are in the habitable zones of many of the stars in this galaxy. And when I look out, and we've imaged already some galaxies out there that have, 150,000, 400,000 stars like our own. And hey, they all have habitable planets in them too. So it's going to be pretty cool. When the Andromeda Galaxy gets a little higher, we'll do some imaging of that again. And that'll make a lot of people happy because we can see the dark lanes in the Andromeda Galaxy as well. When the moon's not out, it looks gorgeous. I have to just tell you that. So, this particular star, I think that we've pretty much finished with this guy. And what I want to do is move on to another one. And don't forget this one. Okay, this one here, Kai Buddhist has actually the potential for planets around that left-hand star, which I think is really, really exciting, and it's really cool. So that's that star. There it is, very tiny, looks like one. And now you know the history. Now you see the separation. You know the actual separation. You know what it would look like if you were there. A star out by Neptune. So when you see little faint Neptune in the sky, and Neptune is actually, Neptune I think is rising if it's not already up. It'll be up soon. And we should look at Neptune just for fun. Let me look it up. Make sure. Let me see where it is. When the moon's out, it's best to look at Neptune when the moon isn't out. But whatever, If we're able to look, we should look.
Yeah, someone came over. I didn't recognize the person. I think they may have came from P&K, and they were asking earlier if you looked at Saturn.
No, I haven't looked at Saturn today.
Mm-hmm.
No, I mean, as I said, if P&K is streaming, they're looking at the moon and the planets. If Bill New York Skywatcher is streaming, he's looking at the wide-angle views of the sky. If I'm streaming, I'm looking at deep sky objects. And we cross over sometimes, and Paul and Keith like when we do that together. But I think that I should offer something different. They should offer something different. We should all have different things. So whatever the mood is, if you want to see deep sky stuff, well, you can come here. If you want to see the wide sky and just sit back and listen to conversation, then you go to Bill. If you want to see the moon, you want to hang out with Paul and Keith, you just go there. Listen to the tunes. All right. My tunes are a little more subdued because I got my big mouth going on and on and on all night long. But hey, this is, where else can you go to get this?
That's exactly what I said. Is that, I mean, from time to time you have dropped by a planet or the moon or something, but
Sure.
That's exactly what I said. It's more deep space objects. I did plug everyone else's channel.
Yeah, that's good.
Bill was on earlier. I said, you were about to stream, and some people that are just already subscribed to you that weren't necessarily at Bill's are over here. So
that's great.
Thank you all for coming. We so appreciate the continued support.
Likewise, and do continue to support Bill and Paul and Keith, because I do, and we're all together in this, and we're all working together in this, and we want to become a one-stop shop for astronomical imagery.
Yeah, Bill was saying that, I don't know if it was earlier tonight or last night, or I don't know. But yeah, no, it's all cross-promotion, so, and Mark's been on both, Paul and Keith's channel and Bill's channel, just drop by doing interviews, so definitely subscribe and hit the bell to all three, because, they're all different things, they're all different places, you get different content, but you see a lot of the same faces. In chat and everything, so it's good, safe environments of all the other places. Oh, it just says stream offline.
Did?
Can you check your hub?
Alright. Let me check.
Okay, back.
Did it come back?
Back, but buffering.
That's weird. Okay, I don't have any.
It's online, but it's buffering. Hold on.
Let me see what's going on.
And offline again.
Yeah, I can see that. That's weird.
And back and buffering.
Yeah, now it's.
Or one of the voice streaming by chance.
It seems to be back online. Is it? It should be online. Is it?
It's online, but it's buffering. It hasn't stopped buffering.
Do a refresh.
Oh, okay. I think we're good. Okay, I think we're back.
Yeah, it's coming back on slowly. I don't know what's going on. I'm going to try and find out who may be doing something.
So, someone else has got to be streaming. Okay, we're back. Yeah. But Skype just gave me a message saying my microphone is really quiet, and all night everyone's been saying that I'm drowning you out, so
it's not.
I'm trying to move my mic and stuff. Buffering. Back.
Yeah,
offline.
Yeah, I'm showing that I'm fine right now. Well, sorry about the technical.
It keeps going offline unless someone started streaming. Could the construction have knocked something out?
No,
could
it's definitely.
I mean, obviously you'd know if the weather changed.
No, it's not that.
I don't know what else it could be.
One of my kids just admitted that he's streaming, and I'm telling him, "You're kicking me off the stream." Yeah, they're gonna have to understand that this is a priority. You know.
Yeah.
Did you tell people to stand by in the chat? You did, yeah.
I did.
All right. How many people were in are watching? Do you know? Amanda?
Yes?
Do you know how many people?
Pardon me?
How many people are watching?
It's not showing right now. The last I checked, it was 17. But it's not actually showing. It's just blank right now. I mean, I'm watching it. It's not even counting as one. I see 12 thumbs up, no thumbs down. That's good. I did say stand by. They're just...
Okay. So I don't know why.
Yeah, just that last sentence that sounded a little bit distorted.
I said one of my kids is streaming.
Yeah, I can't hear you on Skype anymore. You're breaking up bad.
I am? I'm breaking up or not?
Okay, I heard that. Am I breaking up or not? Okay, and now the buffering. It looks like you're back online and buffering.
Yeah, see, now I'm getting a high kilobits per second. It was like downtime there for some weird reason. And now it's offline again. It says 0 kilobits per second. Holy crap.
It's like every time I start to lose your sound on Skype, it starts buffering on YouTube, and then it goes offline.
Wow. Well, I had so much...
Whoever's streaming has to get off, or it's not going to work, even if you open another stream. Sorry, I can't hear you on Skype even.
Hold on a sec.
Okay.
And now I'm at 0 kilobits per second again.
Okay, that's the first thing I heard you say since hold on was 0 kilobits.
That's all I said. I was watching the meter, just trying to figure out what's going on. Yeah. It's hard when you have all this equipment in here doing its thing, and you know, crap starts happening like that.
Mm-hmm.
All right, well, you know what? We're gonna push through, because the last time I saw this happen, I watched the stream later, and I actually had no problem. Like it didn't show any signs of any problem. So
I figured after it uploads it, it'll probably try to smooth all that out.
well, I don't know what it does, but something's going on. You're right. You're right.
Okay, well, it looks like we're back. It says 5 are watching now, so maybe... See, I don't know when it goes offline and then restarts on its own. I don't think it would be creating new links, but
Yeah.
we'll see. If it maintains the, stream consistency, everyone should come back. Okay, we're back up to 8.
Okay.
15. Okay, yeah. Like I said, just as soon as it kind of steadied out, 16. Yeah. Okay, we're good. We're going.
I told him to give me another, another block of time here. So, all right. Okay.
Booking times to stream.
It's like
That's cute.
Book times, yeah. All right, I'm going to go to our next star while we got a chance, and this is going to be Delta Buddhist, which is here in the same constellation. And you'll notice that the telescope actually didn't move too much. And right there on the screen, we can see it. Now, this is an interesting star because this guy here and this star here, the separation, all right, between the components is 104.6 arc seconds, and it's 122 light years away. So you can almost guess what the AU separation is because you actually know from having seen the other one at 145 arc seconds. Well, let's just take a look here. Let's go and bring these into view. Yeah. Yes, it is. What happened, Gabe? Okay.
Oh, so much for anonymity.
Yeah, no, it's okay. I don't mind. Okay, so,
well, both of your kids are super genius too, so they're allowed to relax once in a while. Just preferably not when you're streaming.
Yeah, I can't let them when this is happening, especially when I've got, people that depend on it.
Yeah.
All right, so now we're looking at these two stars right here. And these stars are fascinating, and I'll tell you why. This is Delta Buddhist. This is the fourth brightest star in the constellation of Buddhist. And what's interesting is that the one that you see on the right is a yellow-white star, and it's a G8. Okay, it's a type G8. So our sun's a G2, but it's a normal star. This is a G8 giant, and that's the guy on the right. And as I said, these are 122 light years away overall, and they are separated again by 104.6 arc seconds. So you can calculate the actual distance between them. And the nice thing is that that little star to its left is 8th magnitude, so it's not as bright as the brighter star, okay, obviously, and it's a 3.47 magnitude star, the one on the right, and the one on the left is an 8. So you can see the difference between 8th magnitude and basically 3.5 magnitude on the right. And the one on the left is actually a G0. So our sun, again, G2, and the one on the left is a G0, and the one on the right is a G8. So they flank us. And they're separated by, like I said, the distance of 104.6 arc seconds. And at that distance of 122 light years, you should now be able to figure out the actual distance between them.
I was just waiting for the second number.
Okay.
Hold on. The sad thing is, I know you could do it in your head faster than I can type it into this calculator.
I don't do it in my head. Don't give me that much credit. But I'll give you their orbit. It takes them about 120,000 years to go around each other one time. 122,000 years. And I do know the
Okay.
I know the AU distance, and it's going to be a little bit different from what you're used to.
For some reason, I don't know. Maybe I transposed numbers again. 9.7 can't be right.
Correct, it can't.
Okay.
Okay, so again,
it's 104.6 arc seconds.
Correct.
In between the two stars, yeah?
Yep.
And 122
light years.
Light years away?
Yep. So multiply 104.6 times 122, and then divide that by 206,265.
Hold on, maybe I divided when I was supposed to multiply. Okay. 3,912.
Oh, for the AU distance? That's close, yes.
Yeah, that's what I was trying to figure out. Okay, maybe I divided a second time when I was supposed to multiply on the last time.
Doesn't matter.
Because I knew when it came up that small that I did it wrong.
Yeah.
Okay.
It's around 3,800. Okay, and that's 3,800 astronomical units separating these two stars. That's quite a distance. So now you know that if the star on the right, okay, it's a giant, all right, a G8 giant. That means that the star as a giant might wreak some havoc on the solar system if there is one around that other G0 star on the left. Okay, because giant stars can, or could or could not, explode, and they could cause a planetary nebula. They could explode in a supernova. Depends what the mass of the giant is. So we'd have to follow that star, and we'd have to research it a little bit more to see exactly what the star could cause to that other little star in the area. But at this time, there really is only these stars. There's no suspected planets around these. But again, they're yellow-white because they're G stars like our sun. And it's funny because the different types of stars in the stellar evolution process, like the G8 giant, as opposed to G0 dwarf, which is the fusing hydrogen to helium main sequence star, the differences are actually massive, but the color is still the same because it's the spectral class is just a snapshot of that temperature based on the temperature of the star. And so a giant star that's around 9,000 degrees in its surface, or a small dwarf that's around 9,000 degrees in its surface, both are going to be the same color. So that's just the snapshot. And then what tells us the difference about whether the star is a giant or not is that other class we talked about, the luminosity class, which has that Roman number, like the 5, the V, the Roman numeral. Okay, so a star like this might be a type 2, Roman numeral 2 giant, or supergiants are actually even different than this. There are supergiants beyond this too. So it's kind of, it could also be a type Roman numeral type 3 as well. So that's actually the different types in the luminosity class, as the 1, the 1A, the 2, the 3, the 4, and those are Roman numerals. And then the 5, which is the V, that's the main sequence, regular fusing hydrogen to helium, regular star, dwarf. That's called the main sequence, right? And then you have the white dwarfs down below that. Okay, so those are type 6 VI. So you got a lot going on in this diagram that shows the different types of the stars, different types of stars. That diagram was actually created by Esnar Hertzsprung and Henry Norris Russell, sorry. I kept thinking Wilson, and I'm thinking the Mount Wilson telescope for some reason. And Henry Norris Russell and Ejnar Hirschsprung created this relationship where they plotted temperature and color of the stars versus their brightness, and they found that many of the stars lined up in this really snaky line. It goes down from the upper left to the lower right, in a little snaking line, and that became the main sequence, which is where all the normal stars that are fusing hydrogen to helium normally sit. And so there was a relationship that brought all those stars into some form of commonality between themselves, and that's what the Hertzsprung-Russell diagram, what we affectionately call the HR diagram, shows us, and it became for us. So that was a good guide. So, like knowing color, for instance, you could find some place along the HR diagram where the star was that color, because color's along the bottom, in the O, B, A, F, G, K, M. And you could say, well, the star is an F-type star, but is it an F, main sequence star, or is it an F giant star? It'll be up in the vertical there somewhere, but you can tell where on the diagram it's located. And then under the luminosity, once you figure out the luminosity, all right, then you can figure out whether it's actually a dwarf or whether it's actually a giant of some type. So there's a lot, and its spectra tells us the difference. If a star's spectrum has certain elements in it that we expect to see in a giant, well, then we'd see it there. We'd be looking for hydrogen lines, for instance. We might have stronger helium lines, indicating it's probably a giant. Because hydrogen burning and fusing into helium is the norm. And if we see that we have more helium, well, that's a different story. It might be something different. So that said, that's just a little bit of what we'll talk about in future SkyTour live streams. And I just want to go back and give you that little bit of factoid there. Now, one other little thing I'd like to show you is something that I set up earlier tonight. And I think I might be too late for this object. Yeah, it's already set, but that's okay. I got a few more. I'll tell you what I'm doing in a sec.
Yeah, actually, when you were talking about that chart, Daryl was nice enough to send me a link. It looks kind of confusing to me, but it's nicely sorted. I'm sure if you understood all these terms and what these ratios, or I don't even know what to call them.
Well, you got luminosity, you got
the little grids, yeah.
Yeah, that's
luminosity, absolute magnitude, and then the OBAFG.
Yeah, see, here's what's interesting.
Color.
All of those things relate to each other, so if you know a couple of these things, you can find the third. All right, through a formula or through an analysis on the chart. Sorry, I actually yawned there. I apologize, folks.
Oh.
So that's the only reason there was a delay.
But it's just this. Okay, I understand this. I'm looking at the chart and I can see how you can kind of see follow the grid like you would on a map.
Yeah.
But it doesn't say the yellow part means there's more magnesium and the red part means there's more nitrogen, or I don't know, whatever, you know what I mean?
Yeah, I understand.
I need a chart for that next part too.
I understand.
Yeah.
I understand.
But I'm getting there. I mean, these are such super useful tools to have.
Yeah.
I just don't know where to look, so.
Yep. Now, I know we're doing double stars tonight, and we kind of been, I know there's been a lot of discussion. We had a couple of technical glitches, so I apologize for the delays here and there. When the moon goes away or starts coming up later, we're going to actually spend a lot of time looking for more nebulae, more planetary nebulae, which are the nebulae, the stellar nurseries that I'm talking about. Those are the ones where stars are created. We're also going to spend a lot of time looking for these planetaries I told you about. Planetary nebulae were named so because when Charles Messier was building his list, he didn't want anyone to get confused with these as planets, potential planets that were dim. So he ended up calling them planetary nebulae, but they're actually the remnants of a dying star. It's like, for instance, how our sun might die. Okay, it might slough off its outer layers in later life, leaving some hydrogen and helium clouds around it, and in the end, we would end up with a nebula around our solar system, several light years out. Stars are very, very powerful. Now just imagine that happening billions of times throughout the life of the universe, and you can understand how come there's so much raw material in the elements out there to give us all the materials and give us the Earth itself. It's sort of a monumental thought process you have to go through to actually understand how this all works. I'm going to move to the next star now, and I'm going to go right now. So.
Oh, sorry. Daryl wanted to know if this was a G giant that we were looking at. It's off the main sequence.
Yes. It is indeed. It's actually the G83. It was actually a star that is in fact off the main sequence and has migrated up off the chart, so to speak, off the main sequence. So yes, that's correct.
Is it a Roman numeral 3 or?
Yes, Roman numeral 3. Yeah. Isn't that great?
Mm-hmm.
You are so smart. Now let's do a little video here. There we go. Yeah, let's see. I think. There we go. I'm gonna go here. I think we're going here. Hold on. Let me just double check.
This is gorgeous. I don't know what we're looking at, but I love it.
At the star field?
Oh,
well. I wanted to show people this one more time. We saw it the other night. Oops. And I just wanted to show it one more time. This. And I'm going to just do an exposure here. 0.4 second at 51,200 ISO. And the star we're looking at is right in the middle of the field. Okay. Okay, do you see that star right in the middle? Let me see if I can get this to move over a little bit so you can see it better. Oh yeah, I see someone's writing Morgan Kinan in the chat from here. I'm kind of see that.
yeah, I'm trying to look that up, but it's saying that the site can't be reached, so...
That's the MK system, indeed, but don't worry.
MK system?
MK, yeah.
God, MK.
Now, this, what we're looking at here, okay, and like I said, I wanted to show you one more time before I retire for the evening. This little tiny point of light that we're looking at right there, this is Tabby Star. One more time.
Ooh.
I like Tabby Star. What can I say? I mean, it's really cool seeing it.
I think a lot of people like Tabby Star.
Yeah, and so that's the star right in the center of the field. It's sort of isolated from the others there, and that is the star that's been dimming for over 100 years. And one of these days, folks, that star could be at the center of another alien intelligence, as far as we know. Right now, we don't know. We just wonder about it. But maybe, in 10 years, 15 years, 100 years, 14 years, 3 months, 2 days, 9 hours, we might find the answers. And this star is, to me, the one that actually makes me feel like there's hope for us. Because when I look at a star like this, and I think somebody out there may have actually found the secret of surviving past their nuclear age and managed to figure out a way to get past all of the hurdles that a young upcoming civilization would have or would have to fight. And I'm really pleased that this could be an indicator of that, because that means that we can do it too. And it means that somebody out there has, if Tabby Star is what we think it might be. Now, everyone's being very careful about saying it's a advanced civilization building a Dyson swarm around their star. But until we know better, there's really not a whole lot of other explanations that sort of fit the bill. And that's kind of what we're looking at. We're looking at possibilities here, and that's it, possibilities. So I'm pretty happy to think that maybe Tabby Star is the place for us someday. Neat star, but it goes by the rather nondescript designation of TYC for Tycho Catalog, TYC 3162-665-1. Very boring, but that's Tabby Star. It was a program star. Now, while we're here, we're going to just try look at something that's actually nearby Tabby Star. Something that we've seen before, but we'll just go to anyway, just to check it out before I go offline here. Yeah, those squiggles. Look at the squiggles. That's crazy. There we go. Bam. Right in the center, there where it should be. Okay, let's put it perfectly in the center. That's the telescope who's recentering that, by the way, not me. The telescope's doing a great job.
I'm just seeing the swirls on the screen now.
Yeah. We're actually looking at the Ring Nebula. The Ring Nebula is, of course, a planetary nebula, like we talked about before, but we're also looking at it at 4K, with a 4K video, a live 4K video at high sensitivity. This is at 80,000 ISO. And I know someone said they were confused by my discussion of ASA versus ISO. ASA is older, that's correct, and ISO is the current way we discuss sensitivity. So I'll start calling it ISO just to keep the confusion simpler, keep the confusion less, I should say. All right. So this is the Ring Nebula, and of course, if I were to up the sensitivity, okay, it doesn't get significantly brighter. So when I bring it down, this actually is pretty good sensitivity. But then I'll shut off the video and just go into taking, say, an image, and we'll go down to, say, ASA 6400 and do a let's see what a 4-second photo will do for us here. So now we're taking a photo. Okay, 4 seconds at 6400. And now we can actually see, if we look at the object, we can zoom in, and there we see it. Okay, and if you notice, the nebula itself shows up pretty good, but we don't really see the central star, which is the progenitor, that is the thing that created the planetary nebula. So let's go back and modify our parameters somewhat. Let's go to the next ASA or ISO setting of 8,000, and we'll increase the exposure to 6 seconds. And now let's see what we get. Okay, so now we're doing a 6-second exposure at ISO 8,000. Now when we look at this, we go into the obvious settings here, and we come popping in here. We have a very different situation. We can actually see that central star quite clearly. It's a tiny little star, and it's usually a test of a quality of a telescope to actually see the central star in the Ring Nebula. All right, and Now this is something that, now the ring nebula is fairly bright, but to image it on a full moon like it is now, we have to actually make sure it's almost at the zenith, that is the highest point, and it is. So we can actually go back and take one more photo of this. Let's go right to say 10 seconds. We'll skip right over 8 seconds, go to 10 seconds at ISO 8000. So now we're going to do an 8000 ISO photo for 10 seconds. So it's still your turn. Dun, 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 dun. And then it comes back, and see, when it's overhead, we can actually use lower ISO settings to actually get what we want. But you notice it's still pretty bright. The sky is pretty bright. But notice that the central star is even brighter now. And we can see it now. You see what we do this is visual astronomy that we're doing here. But if we're going to actually turn this into photographic astronomy, what we need to do, all right, is do some of the other things that I do with these pictures. All right, we take these a step further. The next thing we would do is we would take, say, 25 of these, okay, at this setting, and then we stack them together. I've talked about this before. Basically, we align all the stars with each other, align the nebula, and just stack them all together. And you might say, well, wait, that'll make it very bright. And the answer is yes, it does. All right, but then we take it into a special product, something like, say, Star Tools, which is available out there, or PixInsight, or any of these variety of processing tools which can then handle that extra brightness and bring it down to manageable levels. And then you can actually create a masterpiece from a bunch of your digital photos. So this is an example of the beginnings of a masterpiece, but a masterpiece is made one photo at a time, and then you put a bunch of them together, and that increases what's called signal and noise. Because right now when you look at the nebula, you can see some fuzziness around it that are due to the camera noise. Well, you don't want the camera noise interfering with the nebula, okay? So you have to actually add a lot of nebula together to make more nebula come through. And then at the same time, the noise in the background, which is different for every picture, averages out and can be actually subtracted away. And that's something that we do with what's called a dark frame. Once you take a dark frame, it's basically what the camera sees without seeing any stars or nebula at all. It just sees the camera sensor for the same amount of exposure. And that generates a certain amount of noise. And that noise can get wiped off, and so you need to have a number of dark frames, usually 3 times as many dark frames for photos. So if I take 20 photos, I need to take 60 dark frames to come close to having a masterpiece photo. And so that's how we do these things, and it requires patience and great care, trust me. Now, while we're here, we'll go to one more that I think will be interesting to see. And let me just bring up the ISO here.
Again, I think it's so cute, the little tricks astronomers have. If you can see the center star in this ring nebula, you have a good telescope. Well, I think that's funny.
It's something that we've done in the past, ourselves for.
Well, no, it works. I mean, why not? I just said, actually, to check out the pictures from all of the streams, every stream you do, he does put them up in his Facebook group. For some reason, I don't know, it wasn't letting me put the link in, but it's in there now. So, just in case.
Thank you.
Just in case you're on Facebook and for some reason not in the group yet, please join. And he doesn't doctor any of the pictures. He puts them in RAW, and then you can do whatever you'd like with them. Have fun and play with them. And if you find anything cool, let us know. Comment.
Absolutely. And there's a number of them that already have satellites passing through them. You can see what the satellites look like in there as well.
Yeah.
We're gonna go.
Yeah, and if you guys catch any timestamps, let us know. We can go back and check it out and let you know in a future stream.
If we see in the live view. I'm gonna go to one more planetary that's right nearby, the Ring Nebula. It's one that we've seen before, but I'm gonna do it anyway. You can tell it's right near the Ring Nebula.
Well, it's not like it's boring. Oh, well, we've already seen this a handful of times. Yeah, but look at what we're looking at. Never say I know we've seen it before. They're all so gorgeous and so mind-blowing.
Now, you can see what this guy looks like. This is actually just looks like a fuzzy little thing. But let's take a picture. All right. So now we'll take a photo of this fuzzy little thing, and we'll do 10 seconds at let's see, 10 seconds at 10,000. That might be a little long, it might be a little bright, but we'll do it anyway just to see what we get. So we're taking our picture, 10 seconds at 10,000 ISO.
We already have a guess for it from the chat. Is it going to be M27, the dumbbell?
Absolutely correct.
Ooh, yay, Ian.
Alright, Ian. Alright, so there's the dumbbell nebula. And again...
Oh, and Daryl got it in too.
Yep. Yeah, I see that. I have the chat on the side of the screen here, so I can actually see now what they're seeing.
Okay.
Yeah, and you can see the dumbbell now. And again, it's full moon, so I told you that 10 seconds at 10,000 was probably a little bright, and of course you can see that it is. Now, the one thing that's interesting is the dumbbell is a fairly large planetary, yet the star, the central star, is still very visible. You can still see the central star. And the colors are due to the gases being excited. Now, see, there's different kinds of nebulae. Okay, you have emission nebulae, which are the ones that you see in like the M8, the Lagoon Nebula, and those are excited hydrogen that's caused by hot stars that are causing the atoms of hydrogen in the nebula to be excited up a few levels and then drop spontaneously because that's what they do. They don't want to stay that way. And when they do drop like that, you end up getting this reddish glow. That's the H2, or the doubly ionized hydrogen. Planetary nebula are different types of emission nebula. Alright, and they are due to the way the star is exciting the particular gases in the planetary nebulae, and of course the way the planetary nebulae gases are operating on themselves. And then the last type of emission nebula is those in supernova remnants. There's 3 different types. So you have supernova remnant nebulae, you have planetary nebula remnants, and you have stellar nursery remnants, okay, or stellar nursery nebulae rather. All right, and those are 3 different processes altogether from each other, and I think that's a very cool way to discuss it too, because it's neat when you tell people this, and they don't really understand what's going on, and then you say, well, okay, this is what the nebulae do. This is how they work, and there's different types of nebulae. It's very cool. So I agree that it's a lot of fun to look at. And we're going to discuss, by the way, planetary nebulae and what they're glowing for, right? And we'll discuss supernova remnants and what they're glowing for and why. And then we'll do the same thing again with stellar nurseries and talk to you about those. Those you're kind of getting a feel from. We talked about those more often. Those are more the hot stars that are causing the atoms to get excited, and then they spontaneously drop. When they do, they emit photons. They drop in energy, right? And that's typical. Typical in these nebulae. They drop a certain amount, and it's pretty consistent. And we'll talk about that further on other nights. So I'm kind of happy, kind of amazed actually, that we're actually able to see what we're seeing here, because I didn't expect that we would be able to see the dumbbell as good as we did. But the dumbbell is actually almost at zenith too. So as long as we're picking stuff at the zenith, it should be pretty nice. You know.
It's amazing. See, I was gonna say, like, when you first came over here and you're like, well, it's gonna look like a little smudge. Now, you knew what you were aiming for, so you knew what it was gonna look like, but can you ever just, like, randomly kind of slowly go through the sky and you see something that looks like a smudge that you're not sure what it is?
Yeah.
and then just take a picture and.
Yes, you can. And
Because I mean, so much has been mapped out. I mean, what? But you as an astronomer, you would know. You could dissect what you were looking at and figure out what it was, right?
Yeah, I mean, and that's typically what I did for years and years and years. I'd always do that. I'm moving to another object right now, just so you know. You'll hear it now.
Because
Okay, this is another object that's still, it's fairly close to the zenith. And you will see it pull in now. Look at that. This is beautiful. Alright, we've talked about this too before. This is actually a cluster of stars called the globular cluster, the Great Cluster in Hercules. Now, there are other globular clusters that are brighter and have more stars than this one, but this is a beautiful cluster because it's the one we have in the northern hemisphere. Okay, so let's just do this. Let's take one picture. Got a mosquito on me because I crunched one. Sorry. Let's take one nice picture of this. This is the live feed, by the way, live video. That's why I can make the screen shake around a little bit. And I'll come out of that for a second. And let's go and take a picture. We're going to take a photo, and it's going to be 5 seconds at, that wants to be 64,000. I'm going to drop it down to 8,000. So this will be 5 seconds at 8,000. Let's see what we get. This battery's about to die in the camera, so we'll have to change that. I guess pretty good. That's pretty good. Now we want to look at this and check the quality of the star images. And check the focus. And we look for the smallest, faintest star image, and we can see that the star images are actually pretty good. So we know we did a good job here. We know we got good focus. Now this particular telescope has something called a mirror lock, and that means that because I have a large 10-inch mirror, when you focus the telescope, as the telescope moves around, that mirror can't actually move in its cell because it's big and it's heavy. So to prevent that, you have to sort of engage the mirror lock and you tighten it down just a little bit, and then you can actually make sure that you focus only once. And so I've not had to focus more than once. So look at that. These are beautiful. You can actually see the different brightnesses of these stars. And again, this is the globular cluster in Hercules, which I've talked about before, but in case you...
Is it M13?
That is correct. It's M13.
Ah.
And Daryl, did he mention Omega Centauri in there? Is that what I'm seeing?
He said, yeah, I once saw Omega Centauri far down in the southern sky. I was near the Mexican border when I got to see it. Omega Centauri is huge, about as big as the moon in the sky. It was amazing.
Yeah, it's really pretty.
And it's another globular.
Yes, it is. Now this one here, M13, is 23,000 light years away, and Omega Centauri makes this one look like an amateur. Makes this
wow.
One, makes yeah. Well, all right, let's do something here just to show you, because it really depends on the photo you take too. All right, let's do this. I'm gonna go up to 10,000 ISO, and I'm going to increase my exposure to, say, 8 seconds. That risks making it a little bright, but I want you to see that the number of stars that we have now, and versus the ones we're going to see in a second, are going to look different. All right? So let's take a look at the imagery. Okay, so this, not that one, this one, see that image, it looks like the stars are fewer. It looks like a sparse cluster. It looks like it doesn't have a lot of stars. But then we take a little bit deeper exposure. Well, look at now it fills out greatly, and we actually see that there's more stars. All right. So when we go look at this, okay, now we see that the center of this is actually full of more stars, and that's kind of cool. All right. That's kind of cool, and that's what we do. We want to make sure we take an exposure that is just right for the object, all right? And when we looked at this other guy, okay, when we looked at this one and did this picture, okay, we didn't take a deep enough photo. We should have taken a little deeper photo. And just now to complete it, let's go to the same ISO, but we'll now go 13 seconds, which will make it a little bit brighter, quite a bit brighter actually. But we'll see the star images a little bit differently than even that one we just took. Okay, you'll see everything looking different.
Is there a dark Y to the lower left, the propeller?
Oh yeah, you're talking about the just the feature within the nebula? I'm sorry, the feature within the cluster?
I would assume so. Daryl says, do we see the propeller, dark Y to lower left? Is that what he's describing?
Well...
Is that the propeller?
Yeah, I don't really see it. But again, he says lower left, and it depends what kind of telescope. It could be actually upper or lower right, depending on... I don't see it. But he'll tell you. He'll tell you what he's looking for.
Yeah.
Now the other thing is, let's take a look here. So this is the photo we just took. And this is the photo before that. And this is the photo before that. Look at the difference between this and that. You see the big difference? Just exposures change what it looks like. The object looks like it's a sparsely populated cluster. And then we go to here, and it's a rich, exploding snowball of stars. It's just amazing. Absolutely amazing.
Okay, I see you going back and forth now, I think.
Yeah.
Because I mean, again, chat will be synced up. I'm a little behind.
Yeah.
Yeah, I see.
And you'll learn not to even talk about that until, you know, you'll just let it happen, and you'll figure out how to basically just, you know, kill some time until you catch up to what you see. Because you're hearing me live, and of course it's different. And what you see is different. And when they hear you say that, they have no idea what you're talking about because they don't see that actual interaction. But it's okay. It's okay. Yeah, this is beautiful. This is really pretty.
It is. It's gorgeous.
And I like doing I like looking at the raw imagery, you know, the raw live video, you know, because that actually is pretty cool when you can actually show people, like, you know, here's the live, you know, there's a live video feed, you know. I like doing this right here where I can bring out the richness of this cluster just dynamically and live and in color. This is in color. And that's pretty cool. Cool. Wow. Pretty amazing. Pretty amazing. Well, folks, I think this is going to wrap up the stream for tonight. I hope you had a good time. You know, one of the things I want to do is to make sure that I, you know, thank you for all your attendance here, because you really make it happen, okay? So, once again, I want to thank you for coming on board with me in the SkyTour LiveStream, for hanging out with me for a few hours. This has been great. Enjoy it. And this SkyTour LiveStream of July 9th is over. And we will do another one soon. And I really hope that you enjoyed it. Make sure you subscribe. Make sure you get your friends to subscribe. And please do share us to the world on all your social sites, because we would do the same for you. So anyway, I will talk to you again, alright, on the next version of SkyTour LiveStream. Could be as soon as tomorrow if it's clear. Thank you guys. Have a good night.